All right, today you're going to be finding the domain of a function by looking at its equation. And often students make finding domain from an equation a lot harder than it is. So I'm going to tell you a silly kind of story in hopes that it will help remind you what you're looking for and maybe simplify the whole idea. Okay, it begins with a psychiatrist. This psychiatrist, he helps functions with issues. So the psychiatrist, he's in his office and he has a handful of possible patients. The first possible patient is an odd root. Well, the odd root, he comes in, he's like, hey, doctor, I think maybe you can help me out. And he's like, hey, buddy, you're just a little odd. It's all right. It just makes you a little more interesting. We all have friends like you. They're super fun. I can't help you. You need to just go ahead and head on out, and you are fine. All right, so silly, but if you see an odd root, cube root, fifth root, seventh root, etc., those do not have issues. So I'm just drawing him walking out the door. The odd root doesn't have any issues. All right, next is a logarithm. Now, the logarithm, honestly, you are not going to in this class until a little bit further on see logarithms. But I'm going to go ahead and let you know that logarithms do cause some domain issues. So logarithms, you don't want to take the log of 0 or the log of a negative number because you get an error, and we want to only take logs of positive numbers. So logs are possible domain issues. If you see a log in an equation, you might have a domain problem. Okay, then the next one is an x in the denominator. So I'm going to put this x underneath this couch. Kind of silly, I know, but like a fraction bar. So if you have an x in a denominator, that might also cause you a domain error because we never want to divide by 0. Okay, and then we have an even root. I'm going to have this root growing off of this log. All right, even roots, yeah, they have domain issues. You do not want to take the square root of a negative number because you're going to get an imaginary answer. We're only looking for numbers from the number line. So if you have an even root in the problem, that could cause an error. And then it kind of reminds me when we're thinking about what are we going to do if I see an even root with an x underneath it, a logarithm of an x, or an x in the denominator, like what are we supposed to do then? Well, it's a little bit like the advice you got when you were a kid, and you're like, Dad, you know when I press my arm, I'm like, ow, it hurts when I do that. I don't know, maybe my dad was just a smart aleck, but he just was like, well then don't do that. It's really the same advice for each of these patients. If you have a log and you don't want to take a log of the number 0 or a negative number, well, don't do that. Just pick x's so that what you're taking the log of is positive. And for the even root, the advice, if you can't take an even root of a negative number, well, just don't do that. So just make sure you choose x's so that what's underneath the root, that's known as the radicand, stays positive or 0. And then lastly, if you have an x in the denominator of a function, well, you don't want to divide by 0. So don't do that. Don't pick numbers that make your denominator 0. Okay, we're going to look at the algebra, the minutiae of all of it, and go through 12 different examples of finding the domain of some functions. But just keep in mind, please, that if today you see an x underneath an even root, or you see an x in the denominator, well then we need to address those algebraically to find the domain. But if you do not see an x in the denominator, or you do not see an x underneath an even root, well then the domain is going to be all real numbers. I've created this table for you to summarize the rules on how to find domain, provided the equation you're working with doesn't contain any trig. It would be a good idea for you to pause the video here and write this table into your notes. We are going to take a look at several equations and determine the domain of each. But before we did that, I decided to put a Roman numeral next to each one of the cases to make it easier to refer to each. I have written down 12 functions and we're going to find the domain of each. Let's begin by just identifying what domain issue each function has. Let's start by looking for all of the functions that have an x in the denominator. F of x has an x in the denominator, and so does g of x. We keep on looking. K of x has a denominator, but it's just a plain number 7. That's not an x, so that doesn't count. M of x also has a denominator, but there is no x in the denominator, just a number, so not m of x. Keep on looking. We do see another fraction in u of x, but again, the 3 is not an x. We're only looking for the functions where there is an x in the denominator. So v of x has an x in the denominator, and so does w of x. Now let's look at the other functions and see if any of those have domain issue number 2. In other words, an x underneath an even root. The first function that has an x underneath an even root is h of x. As I keep looking, I also see that m of x also has an x underneath an even root. At first glance, you might think that the function p of x has domain issue number 2, but notice this is a cube root. The domain issue only occurs if you're taking an even root, like the square root, fourth root, sixth root, and there's an x underneath the root. So p of x does not have domain issue number 2. Then we notice that r of x has an x underneath the even root. U of x at first glance may appear to have domain issue number 2 because it has a square root. But we're only looking for even roots that have x's underneath the root. And there is no x underneath the even root, so u of x does not have domain issue number 2. Then we see that w of x does have an x underneath the even root. Not only does w of x have an x underneath the even root, it also had an x in the denominator. So w of x actually has 2 domain issues. Domain issue number 3 involves logarithms, and when you take a look at the equations here, you'll notice that we do not see any logarithms. That's because we will not encounter logarithms in this class until much later. So, we're taking a look at these equations, and we have identified those that have an x in the denominator, those that have an x underneath an even root. So any of the equations that do not have domain issue number 1 or domain issue number 2, well, that means they don't have any domain issues. Each of these functions that are remaining do not have any domain issues. This means that all 5 of these functions, the domain is all real numbers, which is negative infinity through positive infinity, otherwise known as all real numbers. You can use this capital R with the extra line as a symbol to represent all real numbers rather than writing down negative infinity through infinity.
I find students try to make domain much more difficult than it is. If you just look at the equation and you do not see an x in the denominator or an x underneath an even root, well then the domain of that function is all real numbers. Our goal is to determine the domain of all 12 of the equations. So now we're going to go back and look at the equations that all had domain issue number 1. I'm actually going to set aside w of x since it has 2 different domain issues. We'll find the domain of w of x last. Okay, so each of these equations have an x in the denominator. The problem that can cause is dividing by 0. So we want to make sure we don't choose an x that makes us divide by 0. So if we follow the rule, all we need to do is set the denominator not equal to 0, and those are the numbers we should not use. Starting with f of x, I'm setting the denominator not equal to 0, so x minus 2 does not equal 0. When you solve, you add 2 to both sides, so x cannot equal 2. Our domain, it just means we can't use the number 2. So let's take a closer look to see how to write this in interval notation. I kind of think about it as reading a number line from left to right. The number 2 is the number that we can't use, but we can use everything to the left of 2 and everything to the right of 2. So if I write this from left to right off the number line, I'm going to go negative infinity, and I'm going to use everything up to 2, but because I want to leave out a 2, I'm using a parenthesis, union. I'm leaving out 2 again, so parenthesis, but I want to use everything after it, so through positive infinity. Okay, so for the domain of g of x, we're going to set those denominators not equal to 0 and solve. When I solve x plus 5 does not equal 0, by subtracting 5, I have x can't be negative 5, and then x does not equal 0 is really already solved, so I just want to leave out the numbers negative 5 and 0. Taking a closer look, how we're going to write this in interval notation, I'm going to put 0 and negative 5 on the number line, and then we're going to leave out the numbers negative 5 and 0, but we can use everything to the left of negative 5, in between negative 5 and 0, and after 0. So kind of reading it from left to right on the number line, we're going to use negative infinity, parenthesis because of the infinity, up through negative 5, parenthesis to leave out the negative 5, union, parenthesis, negative 5 to leave it out, through the number 0, parenthesis, union, parenthesis, 0 through infinity. So these are all the numbers we're allowed to substitute into the equation g of x. And when we substitute any number on these intervals into g of x, we will not be dividing by 0.
Uh-oh, part 1 just finished. Now you got to go to part 2 to finish the lesson.